Going. Okay. Right. Okay. So welcome to the second workshop on gravity, universal gravitation. My style of teaching, I like to keep on going back and revising. That's the way I like to teach. So I'm going to revise quickly. Okay. So in grade 8, you were exposed to the idea of weight. All right. And that weight is the force that an object in a gravitational field of a planet or star or asteroid or some big object is pulled toward its center. All right. So the gravitational field is a region in space in which a mass will experience force due to gravity. So the gravity is about attracting masses. Okay. Now, obviously, as we take matter and we split it up smaller and smaller and smaller and smaller and smaller and smaller, eventually get to atoms, you get to protons, you get to neutrons, and they also have a mass. So they should also be attracted by gravity, and they are, but just the gravity is extremely weak because gravity is not a strong force. It's only strong when you have a very, very big object, okay? So you're exposed to the concept of weight being a force, the force of attraction of an object in a gravitational field toward the center of an astronomical object. However, in actual fact, every particle in that object is being attracted to every particle in this object. And it's actually extremely complex, but we can simplify it. It's as if Mr. D's center of gravity is attracted to the center of gravity of the Earth. Okay, but in actual fact, every particle there is being attracted to every particle there. But we simplify it saying there's a resultant force of the Earth on Mr. D, we call it the weight. It so happens, as we're going to see, it's the mass of the object times the gravitational constant of that planet. So then we looked at the fact that the gravitational constant is the strength of gravity. It's the strength of the gravitational field. Sorry, I should just have added field there. Right, and we discussed how it is dependent on the mass of the source. So that which is creating the gravitational field, its mass, the amount of matter in it, if it increases, it's going to increase the strength of the gravitational field. All right. So the more matter there is in an object, the more in an astronomical object, the more it's going to attract objects in its gravitational field. We also spoke in detail about how the strength of the gravitational field is inversely proportional to the size of the astronomical object. So the bigger the object, it's got more mass. But if you have two objects of equal mass, but one of them's got a smaller radius than the other, it means the one is more dense than the other, you're going to find that the smaller the radius, the bigger the gravitational field. Now, an extreme example of this is a black hole. As the radius of this massive amount of matter decreases when a star collapses, the radius decreases, the gravitational field strength gets so strong that light can't escape it. That's why it's called a black hole. All right, so we looked at the fact that the mass of the Earth is bigger than the mass of the Moon, all right? And on average, on the surface of the Earth, the gravitational field strength is 9.8 newtons per kilogram, and on the Moon it's about 1.67. So we then converged on the fact that, and today we're going to focus more on this, is that the strength of the gravitational field is proportional to the mass of the source and inversely proportional to the square of the distance or the radius of that planet. Then, using Newton's second law, which you guys haven't done yet, hey? So Newton's second law says that an object that experiences a net force will be accelerated in the direction of the force. All right? So, and it's going to be equal, the acceleration is going to be proportional to the force and inversely proportional to the mass. That lands up in the form of F net equals mass times acceleration. But your weight is mass times, I said acceleration, but gravity constant is also an acceleration. So as a matter of fact, gravity, the gravitational constant, can be measured in meters per second squared or in newtons per kilogram. Now, when you do Newton's second law, please remember that you can also view this as F net equals mass times acceleration, weight equals mass times gravity. Right, now, when you substitute this in for gravity, then you get that your force of gravity is the mass of the object being attracted times the mass of the source over the radius of the object squared. Okay, so now this is all revision. What Newton said was something quite amazing. Newton said that gravity was a universal phenomenon, and he introduced the idea of a universal gravitational law. Remember, I said in the first workshop that this was the first time formally that there was an official statement made by natural scientists, natural philosopher, because that's what scientists were called at that stage, that the way the apple falls is the way the moon falls, is the way the earth falls around the sun. That the laws of gravity on Earth are the same as the laws of gravity in the Andromeda galaxy and the laws of gravity in Sagittarius A star black hole. And that was a massive statement, because the belief was that the laws of the universe were not the same everywhere. And so this is a very important law. Every particle in the universe exerts a force of gravitational attraction on every other particle in the universe, and the force is directly proportional to the product of the masses. Okay, mass 1 times mass 2. Right, as this product increases, the force of gravity increases. But it's inversely proportional to the square of the distance between their centers. So if you take the distance between the center of one object and the center of another object, as the distance increases, the force of attraction falls off. And when you put them together, you get this statement. The force of gravity is directly proportional to the product of the masses and inversely proportional to the distance of the square of the distance between them. And this took us to that formula. And this is the mathematical form of Newton's universal law of gravitation. That the force of gravity is equal to the gravitational constant, the universal gravitational constant, which is 6,67 times 10 to the negative 11, which in itself tells you how small that is. That is tiny, ladies and gentlemen. If you approximate that to 10 and you multiply it by that, you get an order of 10 to the negative 10. That is 1/10 billionth. That's tiny. The only way you get a significant, the way you get a significant force is by having one of these masses being significantly big, astronomical. Okay, so what I did was, we looked at using Newton's law of universal gravitation in a mathematical form, and what we did is we did a calculation of, I think it was my mug, and I think it was my Erlenmeyer flask with coffee in it, and we worked out that we actually got a tiny force. And that's why they don't attract each other. Well, they do attract each other, they just don't see it. Okay. Okay. So this force of attraction. But if I drop this, which way do they go? Toward the bigger object, which is the Earth. So they do get attracted to each other, but the force of attraction here is that. But the force of attraction of the Earth is much bigger, so they go down. Then we looked at introducing an astronomical object, namely the Earth. We looked at the mass of the Earth, and we go, okay, that's a big mass, 10 to the 24 kilograms. All right, mass of an object like Mr. Duffield, Mr. D, 80 kilograms. From the center of the Earth, I'm standing at about 6,500 kilometers. Let's work out the force. we worked out the force, and the force of attraction between me and the center of the Earth was 783,082 newtons. But when I worked out W equals mg, grade 8 way, I got the same answer. So this is a more complicated way of working out the weight. The weight is the force of gravity. Okay, then what we did is we looked at what happens if you've got two astronomical objects. What happens if you have two astronomical objects? Let's take the moon and let's take the Earth. Now, remember that Newton's universal law of gravitation says it's the force of attraction is directly proportional to the product of the masses and inversely proportional to the square of the distance between the objects. So you have to take the radii into consideration because the radii contribute to the distance between the two centers. And then we noticed, now we get a big force. And the reason why we get a big force was we're dealing with big masses. Enough force to keep the Earth and this moon in the same system. Okay, that's what we've done thus far. Then I gave you these to do. All right, I think it was just, I didn't give you 6, and we're going to get to 6 now. All right?
So some of those answers were wrong.
Because they use G equals 10. It's from the IB. Okay, how wrong were they? Okay, all right, which ones?
I think number 1 is.
Okay.
Number 1 is.
Okay, yes.
I got everything right, basically, except 2.2.
Okay, all right. Okay, calculate the force of gravitational attraction between a mass of 80 kilograms and a mass of 24 kilograms placed 2 meters apart. There's nothing complicated about that. But let's take the number 2, all right? Let's take number 2. I'm going to do number 2, all right? And let's see what we get, okay? Now, unfortunately, and I say this, the reason why you're not getting it because you haven't done Newton's second law of motion yet. The reason why you're not getting it is because you haven't done Newton's laws. This is the 4th law. You haven't done the first 3 yet. All right. Normally, when we do this, you've already done the first 3 laws. It just so happens that's the way it's worked out this year. Not the end of the world, not the end of the world. So let's do this. All right. So let's look here and we go, all right. So we've got 2 space capsules of equal mass. Eh? So we've got space capsules. Tell me, are they astronomical? They're not, okay? They are 30 meters apart, and they haven't given us the dimensions, the physical dimensions. So we are going to put that the distance between them is 30 meters. By the way, it doesn't matter whether you use D or R, okay? It doesn't matter. We are told that they each have the same mass, and the force between them, along the line that joins them, is 2,0 times 10 to the negative 7 newtons, 2,0 times 10 to the negative 7 newtons. Now, here too, I'm using Newton's third law. So Newton's third law says the following. If Mr. D is attracted to the fire extinguisher, okay? Well, let's use the TV so that they can see. If I attract the fire extinguisher, the TV, the television, with the force of gravity, and let's say it's 10 to the negative 15 newtons, I attract the television to me. Newton's third law says the television attracts me with the same magnitude force, but in the opposite direction. It's called an action-reaction pair. So let me give you an example here. Can you see that bottle is stationary? All right? Now, The force of the bottle on the surface is equal in magnitude to the force of the surface on the bottle keeping it up, but they're in opposite directions. Okay, now, as I apply this upwards, the force of the bottle on my hand and the force of my hand on the bottle are the same, even though it's moving. But why isn't it in equilibrium? Because they act on different objects. Newton's third law is not equilibrium. All right, so you will always have equal forces, interacting forces between objects that will be equal in magnitude but opposite in direction, but they always act on different objects. So this capsule is attracting that capsule with this force, and this capsule is attracting that capsule with this force. So when they talk about the force of gravity between them, it's talking about both those forces being 2 times 10 to the negative 7 newtons. The force of gravity occurs on both of them. Are you clear on that? Don't divide them in two, okay? The force of gravity is the force of this one attracting that one, and the force of this one attracting that one. That's the force of gravity. So, it asks us, what is the mass of each capsule? So we go F equals G, mass 1, mass 2, over the distance squared. 1 mark for the formula. All right, then it says, okay, F equals G. What is G? 6,67 times 10 to the negative 11. Correct? Is that what? I just sometimes I've got to be careful of 6,63 or 6,67. Okay, because Planck's constant is 6,63 times 10 to the negative 34. You can get mixed up. Okay, mass 1 is mass. Mass 2 is mass. Distance squared is 30 meters squared. All right, but now they've told us that the force of attraction is 2 times 10 to the negative 7. 2 times 10 to the negative 7 newtons. All right, so now we've got an equation. So we can say, okay, so I've got 2 times 10 to the negative 7. I'm going to multiply by 30 meters on both sides. So times by 30. I'm going to divide both sides by 6,67.
So shouldn't the 30 be squared?
Is it 30 or is it 20?
No, it is 30, but shouldn't it be 30 squared?
It should be 30 squared. Absolutely, 100% correct. Thank you, Tamlin. Should be 30 squared. Mass times mass is mass squared. Absolutely, well done. All right, and it's over 6,67 times 10 to the negative 11. And so we can get that mass squared equals, mass squared is 2 times 10 to the negative 7 times 30 squared is 900 divided by 6,67 times 10 to the negative 11. And that gives us that this is 2698650,675. We're going to square root both sides. So we square root it, and we get that the answer, the mass of each of them is 1642,757 kilograms, which is approximately 1,6 tons. Not that we need to put it in that, you leave it like that.
So on our calculator, it got 1.64, well, obviously with the decimals, but we round
Actually, it doesn't
times
matter.
10 to the negative 8. That's why I got confused. Yeah.
Okay, let me just do this again. So 2 times 10 to the negative 7 times 30 squared, all right, divided by 6,67 times 10 to the negative 11. Okay, now here's my question. When you're dividing this, are you saying divide by 6,7 times power to the negative 11? Because if you do that, then it pops it upstairs. Or are you using the EXP button? Okay. The way you're inputting this on your calculator.
We're saying times 10 to the power of -11.
If you do it like what button are you using?
The actual 1-0. Like what I did is.
Are you using that button?
No.
That's why it's doing it. So what happens if you don't use this button, then you put in brackets.
Wait, so.
Then you put in brackets, because if you use the times 10 to the x button, what it does is BODMAS, it's programmed with BODMAS. It divides this and takes this and times it upstairs.
So should we rather do that?
So my suggestion to you is, if you're not going to use the times 10 to the x button, this one, then when you input it, put a bracket around both.
I do.
But you didn't this time.
No, but I did for all of them. I checked on the calculator. That's
Okay.
why I was so confused.
I don't believe you're doing. I believe the way you're inputting it, you're putting this upstairs. What's your answer that you're getting? Times 10 to the?
-8. That's why.
Times 10 to the -7. 30 squared is 900. That's probably, that's around 10 to the 3. 10 to the -4 times 10 to the -11 gives you 10 to the -15. What are you getting?
-8.
No, it's wrong. There's something you're doing wrong mathematically. Okay, I can't. We've got to move.
Yeah.
Okay, I think it's just showing how you inputted it.
Like it's over here somewhere. Like on my calculator, I didn't know calculating.
If you divide
No, but
this,
even without
no,
the
wait. If you divide this into that, the 10 to the -11 is going to become 10 to the +11. You shouldn't be getting 10 to the -16.
I don't know how.
Okay, because you're not dividing this properly into that.
Yeah.
That's why. Do it again and you'll see.
Even without the brackets, you still get that on.
Okay, what you've done is you've made a mathematical mistake. It's not a physics mistake, it's a mathematical mistake. Okay.
It could just be because.
Yeah, it's a mathematical mistake. Yes.
So when I do these problems, then I put my calculator in scientific.
Yeah.
But then I get an answer without all those numbers. Like without all those decimals.
Guys, we shouldn't be fussing about arithmetic
No, but I'm saying
in grade 11. If you put it on side, okay, what is it fixing on? How many decimal places? That's your problem. It's fixing everything to 2 decimal places. Don't fix it. You want to run all the decimal places. Okay, ladies and gentlemen, I'm not a calculator guy. Okay, I'm not here to teach you calculator work. Okay, we're never going to finish what I need to do today. We can talk about that, Imra, afterwards. Okay, all right. I'm not a guy who knows all the calculators. Just don't fix the decimals to 2, because then what it does is that it creates a problem later on. In grade 11 and grade 12, you must run all the decimals and round off to 3 decimal places in the last step. Okay, I'll come and help. I'll help with the calculators later on. I want to get through the work I need to get through, and then we can look at the calculators individually. All right, okay. Now, unfortunately, it's the first time ever I'm teaching this, and you guys haven't got a clue about Newton's laws, which is problematic to a point. So, okay, to get the acceleration given to each capsule, all right, let's just quickly diverge into Newton's third law. If I've got A and I've got B, Newton's third law says, if A acts on B with F, then B acts on A with minus F. And the minus is the sign, is the direction. So if I have A acting on B, force of A on B acting in that direction, then Newton's third law says there's a force originating at B acting on A, which is in the opposite direction. So the force of A on B will be the negative of the force of B on A. This is Newton's third law. It's what's called an action-reaction pair. So when you've got objects that are gravitationally attracted to each other, they're always going to have the same gravitational force, magnitude-wise, attracting each other, but they'll be acting in opposite directions. Okay, that's Newton's third law. All right. Newton's second law in mathematical form. Newton's second law says, if I have a mass and I apply a net force on the mass, it's going to cause that object to accelerate, right? And the acceleration is going to be such, that F net divided by the mass will give you the acceleration. It's not quite the way it's stated. It says the acceleration produced by the net force will be directly proportional to the net force and inversely proportional to the mass. So if I'm applying a net force on the same net force on two different objects, one is a motor car, the other is a motorbike. The motorbike can accelerate faster because it's got a lower mass. All right. As you decrease the mass, you increase the acceleration with the same net force. As you increase the mass, you decrease the acceleration with the same net force. Now, this Newton's second law is in mathematical form F net equals mass times acceleration. Right? The mass must be in kilograms, the acceleration in meters per second squared, and F net must be in newtons. But if you look carefully, this is the same form as W equals mass times gravity. Okay. Right. Now, when we come to the problem with the satellites, with the objects in space, the space capsules, each of these objects is in space. They are not experiencing friction, normal forces. On each of these objects, the net force is the gravitational force. So therefore, for 2.1, we've got this. For 2.2, we can say that F net equals the mass times the acceleration, all right, that each of them is experiencing. This is true for each of these masses, all right? So each of them are experiencing a net force of 2.0 times 10 to the negative 7 newtons. And the reason why the net force is the gravity force is because there's nothing else acting on it. They're in space, all right? So we've got the mass. No, we don't have we have the mass now because we worked it out. 1,6 times 10 to the 3 kilograms. As you can see, I worked it out more accurately. So we've got F net. F net is 2,0 times 10 to the negative 7 newtons. The mass, I'm going to use 1,642,757 kilograms. Right? And that is multiplied to the acceleration. So therefore, the acceleration is going to be 2,0 times 10 to the negative 7 newtons divided by 1,642,757 kilograms. And that's going to give us an answer of 1,642,757. And that gives us that the acceleration is tiny. It is it is 1,217 times 10 to the negative 10 newtons per kilogram, but an alternative unit is meters per second squared. They're equivalent. All right? So when you talk about gravity as an acceleration, you use meters per second squared, and I'll tell you why. Because acceleration is change in velocity over change in time. Velocity is change in position over change in time. So this is meters per second. This is meters per second per second. Meters per second is meters per second squared. Okay, so when it comes to gravity, you can view it as an acceleration or as a field intensity, as we're going to do now when we look at the field, gravitational field. Okay, done a fair amount. Any questions on this at this stage? Okay. The method, not the calculator work, the method. Okay. Calculator can get sorted out. The actual physics, are we okay with the physics? All right. Cool. All right. If we go back here, okay, this is an important one. We love to ask altitude questions. Who have you got this right? It's an altitude question.
I think like 205.
You get 205?
Yeah.
Okay, so let's try this. It says an astronaut weighs 800 newtons on the surface of the Earth. What will his weight be at an altitude equal to the radius of the Earth? Now, I'll tell you why you've got a slightly different answer. This question, this answer comes from IAB, where they used to use G as 10. So to get the mass, they divided by 10 instead of dividing by 9,8. So your mass is going to be a little bit bigger than what they used. But I want to do this one, all right, because this is really important. Okay. Not the one I wanted. Oh, I thought I'd taken my bad. Sorry, let me go back here. I thought I'd fall. Okay. Save to photos. Apologies for that. Why is it doing this now? I'm picking up a problem here. Okay. Something weird's going on here. I think it's got to do with the fact that I might be on classroom. So we're going to go. We'll do this. Apply. Okay. I think it's going to work. Right. An astronaut weighs 800 newtons on the surface of the Earth. So here is the Earth. Okay. Here stands the astronaut. And the astronaut has got a weight of 800 newtons. Okay? On the surface of the Earth, G is 9,8 newtons per kilogram or 9,8 meters per second squared. Okay, you guys have done acceleration, right? Of course, you've done vertical motion, so you know about acceleration. Cool, that's good. All right? Okay, we know that weight is mass times gravity. We know this from grade 8. Okay, so therefore, the mass of the astronaut is the weight of the astronaut divided by gravity. This is going to be 800 newtons divided by 9,8 meters per second squared or newtons per kilogram. So when we do that, we're going to get 800 divided by 9,8. That is going to give us a mass of 81,633 kilograms for the astronaut. Okay, are you all okay with that? Okay, you're okay with that? Cool. All right. Now, altitude problems, very, very important. I think this was number 4, eh?
Yes.
Okay. Now, it says, what will his weight be at an altitude equal to the radius of the Earth? Right. So now, can you see that here? The distance between him and the Earth was 1 radius. Okay. If we now take the dude and we take him or her into space, there's the radius of the Earth, and we take him to another radius above the Earth. Now that's quite far. I mean, that's about 6,500 kilometers into above the Earth's surface. Okay. Then we put the astronaut there. There's the astronaut. And we assume it happens very quickly, so his mass doesn't change. The guy hasn't put on weight, he hasn't eaten more food, he hasn't gone and lost a lot of weight in order to enter Mr. USA competition or whatever, okay? Basically, you take the guy and you put the dude there, theoretically. So his mass doesn't change. His mass is 81,633, kilograms, my bad. Kilograms. Okay. All right, we're okay with that? Okay. Now, if we look at the distance between him and the center of the Earth, the distance now is 2 times the radius, which is 6,3 times 10 to the 6 meters. So the distance now is going to be 12,6 times 10 to the 6 meters. All right? When we worked with his weight was the force of attraction between him and the center of the Earth when there was a distance of 1 radius between him and the center of the Earth. Now we've doubled it. Okay. So what we do now is we say, okay, well, if we look at what the force of attraction is going to be there, we can say the force of gravity is going to be G. The mass of the astronaut, we call him mass 1. The mass of the Earth, we call mass 2, over the distance squared between his center, which is around his belly button, and the center of the Earth. So now we go, okay, so the force is 6,67 times 10 to the negative 11. You will not be expected to remember that number. That is a constant that's on your data sheet. Times the mass of the astronaut, which is 81,633 kilograms. But now the second mass is the mass of the Earth. All right? And they've given us the mass of the Earth. It's 6 times 10 to the 24 kilograms. 6 times 10 to the 24 kilograms. And the distance is 12,6 times 10 to the 6 meters. And that is squared. So if we work that out now, 6,67 times 10 to the negative 11 times 81,633 times 6 times 10 to the 24 divided by, now, if you're not sure, then I would put in a bracket like this. Believe you me, lots of us make mistakes under pressure. I can remember in my 3rd year quantum mechanics exam, right, I forgot that when you add fractions, you need a lowest common multiple. And I couldn't understand why the darn thing was working out. It wasn't working out after 4 pages. And I went back and realized I'd made a mistake on primary school level mathematics. I didn't use the lowest common multiple for the denominators.
I wrote down the brackets, but I didn't put them in the calculator.
You see.
Sorry.
Okay, no, that's it. So what happens if you don't do that and you don't use this specific dedicated button there, then it takes that 10 to the 6 and it puts it up there. Because remember, BODMAS is brackets of division, multiplication.
Yeah.
Okay, that's fine. We learn from our mistakes.
Sometimes I make such stupid mistakes, I can't even see it. Like out of pressure, my finger will think I pressed the point, but I'll have, say, 126 times 10.
You do know that's why they call them mistakes.
Yeah.
Okay, because we don't do them on purpose. All right, and so we get here 205,779 newtons. All right? Are we okay? Yes.
The only thing is for the math when we worked it out in the beginning, are you allowed to round to it or do you leave it?
Okay, so my advice to you, and I'm sure Dr. Rousseau and his team will give you the same advice. If you're going to round off to 3 decimal places. All right. The reason being is that the standard rounding off in matric is 2 decimal places. But they can be very, very finicky about how you round off to 2 decimals. So rather round off to 3. But my advice is when it comes to, for instance, like the mass here, all right, can you see I work to 3 decimal places? There will be an error in my rounding off. But more than likely, the error is going to be in the 3rd decimal place. But they look at the 2nd decimal place. So you see, I'm going to be building in a buffer. Okay. But don't round off here to 2 decimals. Round off to 3. Ideally, leave. Don't round off. Okay. All right. Are you okay with this? Can I show you something? Okay, now it's not going to work out exactly, and I'll tell you why it's not going to work out exactly. Because when you work out 9,8, the values for the mass and the radius of the Earth are slightly different. Because you know the Earth is not a perfect sphere. Okay, let me show you something. If I take force versus distance, and I go to the Earth's surface, this is the center of the Earth. This is the radius, one radius from the center of the Earth. This is the surface. Okay? We were told that at the surface, that particular object was experiencing 800 newtons on the surface. Okay. When we took that object to an altitude of 1 r, that means 1 radius above the surface of the Earth, then it was about 200 newtons. Let me show you why. You see, ladies and gentlemen, isn't force inversely proportional to the distance squared? What happens when I double the distance? A factor of 1/4 comes out. If I double the distance, I 1/4 the force. What's 1/4 of 800? 200. Proportionality. I could have done this with proportionality. So if you double the distance, you have 1/2 squared in the denominator is 1/4. Your force goes down by 4. And if we went to 3r, then what do you think your force would be? Well, if you take 1/3d squared, this becomes 1/9 d squared, which means 1/9 of the original force. What's 1/9 of 800? 800 divided by 9 becomes 88,889. And this leads to the proportionality problems, which in my opinion are the toughest problems that you guys face, is the multiple choice where they say, what happens when you double the mass of the one and half the distance of the other? All right. Then you've got to use proportionality because they don't give you values. Okay. But I'm going to give that to you. I'm going to show you how to do one of them. I'm going to give you a few to do for next week because I want to go into working with the gravitational field strength. Okay. So this is very important. Okay. Now, if we go here, this is the type of problem I'm talking about. An astronaut of a mass 80 kilograms lands on a planet with radius of which is half that of the Earth and the mass of which is 3 times that of the Earth, what will the force of attraction that this planet has on him? This is exactly what I'm talking about. Have they given you the mass of the Earth? Have they given you the radius of the Earth? Mm-mm. But we do know that on the Earth, his mass times 9,8 is going to give you the force of attraction on the surface of the Earth. Okay, so I'm going to do this one, and then I'm going to give you these to do for next week. Just that question. Okay, but I need to go on to something else as well. So let's take this one. Okay, let's take this one, and I am going to. It's not working. I don't know. It's going into some funny mode. Some funny mode. Okay, I'm going to take this one. Okay, apply. Done. Okay. An astronaut of mass 80 kilograms lands on a planet, the radius of which is half that of the Earth, and the mass of which is 3 times that of the Earth. What will the force of attraction that this planet has be on it? So let's take a look at the Earth, the blue planet. Let me use blue. There is blue. There is the Earth. This astronaut stands on the Earth, and he's got a mass of 80 kilograms. All right. And we want to know, what is the force of gravity, his weight on him? Can you please work that out for me? Can you work out his weight force for me? You've got his mass, and you've got that G on Earth's surface is 9,8 newtons per kilogram. Work out his weight. You know he's on the Earth. G is 9,8 on the surface. So his weight is going to be mass times gravity. Agreed? All right, so his weight is going to be 80 kilograms times 9,8 newtons per kilogram. And that's going to mean that if that guy was on the surface of the Earth, his force, the force with which he'd be attracted, is 784 newtons. That would be the force of gravity on him. Okay, so let's call this is the mass of the Earth, and this here is the radius of the Earth. It's the planet we live on. You're cool with that? 80 kilograms, which by the way is about my mass. Okay, all right. That's what on average every day I experience. 784 newtons acting down. Now, the astronaut gets taken to a planet. It has 3 times the mass of the Earth, but it has half the radius. We've got a much denser planet. 3 times the mass in a much smaller, okay? So what happens is we go to planet X. Okay, planet X, the mass of X is 3 times the mass of Earth. You agree? All right. And the radius of planet X is half the radius of Earth. Okay. You agree? Okay. Now, this astronaut's mass is 80 kilograms, and the force that he or she's going to experience, the force of gravity on X, so let's call this Fx, is going to be G mass of X times the mass of the little astronaut over the distance between the astronaut and the center of planet X. You agree? Okay. So we say, well, okay, so the force on planet X is going to be g. The mass of the planet is 3 times the mass of the Earth. His mass stays the same. The radius of planet X is the radius of the Earth divided by 2. Okay, so if we work this out, Fx equals 3g mass of the Earth times the mass of the astronaut over re squared over 4, because re squared is re squared, 2 squared is 4. But we tip and we times when we divide by fractions, don't we? So this is going to be f of x equals 3 times 4, because we're going to tip and we're going to times, g mass of the Earth, mass of the astronaut, divided by r Earth squared. So this is going to mean that fx is 12 times this. But what is that? Well, isn't this the force of G on Earth? Isn't the weight, can't we write the weight differently as G, mass of the Earth, times mass of the astronaut over the radius of the Earth squared? We worked it out as mass times gravity, but that thing equals this thing. This thing and that thing are the same. It means the force on planet X is 12 times the force experiences on Earth. Because this equals that. So now this is quite algebraic, and that's why I say to you, these are the ones that trick up students. But can I show you a cheat method that you can use in multiple choice questions?
So then how did they get 9.6
How did we get?
kilometers?
Okay, absolutely, because now, what was his weight on the Earth? Thank you, Michaela. What is the weight on the Earth? 784 newtons. So now we need to take Fx and we're going to times it by the force of gravity on him on Earth, which is 784 newtons. And when you times those two together, you get, okay, it's not, you're going to get 9,408 newtons, which is 9,408 newtons. The reason why they got a slightly different value, because in that textbook they used G as 10. But this is the method. Okay, now I will admit that that method looks intimidating if you're not really a mathematician. Can I show you a cheat method? We know that force is proportional to mass. We know that force is proportional to 1 over r squared, or 1 over distance squared. Okay, so we know that force is proportional to mass over distance squared. We are timesing by 2. No, not timesing by 2. The mass is of the Earth timesing by 3. And we're dividing by the diameter by 2. We're halving the diameter and we're timesing the mass by 3. Are we changing the mass of the person? So the mass of the Earth is changing by 3, factor 3. Mass and the radius of the Earth by half. Work this out. Isn't this 3 over a quarter? Isn't this 3 times 4 over 1? Isn't this a factor of times by 12? Okay, now, from experience of lots of years of teaching this, this is where you need to go and you need to sit down with a nice cup of coffee or a nice bowl shake at home, and you need to practice these things. Because you've got to get your mind to work with these things, with these problems. Okay, so I've shown you a way of doing it. I will post this, obviously, all right? But because they haven't given us the mass of the Earth and the radius of the Earth, all right, we have to work with it algebraically. Okay, tricky. Okay. All right, I'm going to give you those others to practice, but I want to now go on to the last few minutes of this workshop. I've got about 15, 20 minutes left. I don't want to go much past 4 o'clock, okay? All right, okay. Be reasonably...
So the 3 times 4 over 1 doesn't make sense to me.
Okay, if you look, yeah, if this is on Earth, Michaela, okay, let's put the mass of the astronaut there. All right. Are we changing the mass of the astronaut? No. So when it comes to how it changes, the mass doesn't have. What are we changing? We're changing the mass of the planet, and we're changing the diameter of the planet. Oh, not the diameter, the radius of the planet, the distance between the center and where this astronaut is standing. What are we doing to the mass? We're timesing it by 3. What are we doing to the radius? Halving it. And now the mass sits upstairs. So the only thing we're changing upstairs in the equation is we're multiplying the mass by 3. The mass of the object is we're multiplying by 1 because it doesn't change. Downstairs, what are we doing? We're timesing the radius by a half. But the half sits in a square because remember it's dependent on distance squared. So the factor, the mathematical factor that we're looking for is 3 over a quarter, which is 3 times 4. So what it means is the overall expression is being multiplied by a factor of 12. Okay. I don't expect you to get it in this sitting. All right. Now, Mr. Himon posted a very, very nice, he's got a very nice summary of this. I don't want to give you the summary yet. I want you to struggle with it first. I don't want you to do rote learning. I want you to understand. Yes.
So can you just go back to, okay, so when change that part of the formula to the f of g on Earth, right?
Where, yeah.
No, the step below, the circle, the yellow circle, right? So that is the formula that we normally work with.
Yes, that's for the force.
Yeah.
Yeah.
So the f in the formula that we normally use, is that the gravitational
Yes.
force?
Yeah, this F is a gravitational force. Yeah. So when you're working in the context of this equation, that is the gravitational force. Yeah.
So it's a different color.
Yeah, it's the gravitational force changes because the mass of the planet's changing and the radius of it's changing. Okay. Right. I think it's going to make more sense when we go and we do. I want you to do for next week. Number 6. Do number 6. You're going to struggle a little bit with it, but you have got the answers there. All right. Okay. It's one of those things you have to sit down and you've got to arm wrestle. It's like you've got to struggle with it yourself. Okay. All right. Are we cool? Okay. Now, this is the next thing. We have dealt with the gravitational field as a region in space in which a mass will experience the Earth's gravitational force. What is interesting is, okay, and we don't use 10, we use 9,8. All right, we use 9,8. Okay, if you look at the way the gravitational field's strength varies, on the surface, it gives us a value of 9,8. This part of the curve is proportional to 1 over distance squared. If you take a look here carefully, can you see at double the distance, the g value goes to a quarter. If you go to a third, if you triple the distance, Then 1 over 3 squared is 9, so it should be 9,8 over 4. Okay, this is basically g over 4, g over 9, g over 16, and this is g. So as you increase the distance, because your g is equivalent, and your force of gravity is proportional to the inverse of 1 over d squared. If you double it downstairs, you're going to get a factor of 4, right? Because 2 squared is 4. If I triple the distance, all right, downstairs, what's 3 squared? 9. And if I quadruple, then what's 4 squared? 16. But it's downstairs. So this is kind of like a hyperbola, but not quite, because it's to the square, not to 1 over d. It's not like y equals k over x. It's like y equals k over x squared. But here's something totally crazy. If you start to dig into the Earth, it becomes linear, to the point that at the center of the Earth, your g value is 0. And the reason for that is, as soon as you go into the Earth, you've got solid all around you. And it's pulling you in different directions. And the resultant g is actually less than on the surface. And when you get to the center of the Earth, which you can't physically, but if you were able to, you'd be weightless, because you're being pulled equally in all directions. So you have your resultant gravitational force is 0. But we don't work with the linear decay of gravity in the surface. That's for university. All right, so now let's move on. If you look at the gravitational field intensity, you need to write this down. The gravitational field intensity is defined as the force experienced, per unit mass by an object in a gravitational field. Right. This concept is super important, not only for this, but for electrostatics as well. Because in electrostatics, we're going to work with the electric field intensity, which will be the electrostatic force per unit charge. Yeah, we're working with the gravitational field strength as the force per unit mass. Now, if you look at this, we've already worked with G equals weight divided by mass. Well, your force of gravity is the weight. Okay. Now, if you go and you take Newton's mathematical form of Newton's law, we go as follows. We say G equals, if we do the following, sorry, just copy that down, and then I want to prove it to you. All right, I want to prove it to you. So this is an important definition here, okay? So this is the gravitational field intensity. Another term for it is the gravitational field strength at a point in the field. Okay. Right. Now, this is beautiful. Okay, because it's super easy to use and prepare and to prove. Okay, so what I'm going to do is I'm going to say, okay, so we know that G equals the force divided by the mass. So let's say we have an object, and let's say this object is an astronomical object, and we say that this is the source of the gravitational field. Okay, and at a particular point, okay, you've got the gravitational field, and let's say at a particular point there, let's call this point X. The value for G is little g. Okay. Notice I haven't necessarily put it on the surface of the Earth. You see that? This doesn't have to be the Earth, it can be an astronaut. Okay, so I've got a question for you. At this point right here, is there a force? force field, but there ain't a force. Because for there to be a force, you need to have something for the field to act on. You need to have a mass. You see, force is mass times gravity. So if you have the G, but you don't have the mass, what's 0 times G? So a force and a force field are not the same thing. That is a very, very, very difficult and very important concept. So at this point here, it's a point. There's no mass. But now, let's say, as soon as I put a mass there, I get a force. And that force, F, right, is going to be G, the mass, M, times the mass of the source, okay, over the distance, which is the distance between wherever this point is in the center, let's call that D, over D squared. This is, but this is divided, it's per unit mass. But ladies and gentlemen, the masses cancel. Oh, Galileo, you were right. Whether I take a cannonball or whether I take a cricket ball, I sit on a very tall building and I drop them, they fall at the same acceleration because they are independent of the mass of the objects and completely dependent on the mass of the source. So the actual G value is equal to G, which is the universal gravitational constant, times the mass of the source of the gravitational field over the distance squared. But ladies and gentlemen, this is for G. G is dependent on the mass of the planet and source over the distance squared. But this is not a force. The only time you get a force is when you put a mass there. When you put a mass there, then you get a force. Okay, this is also a concept you need to sit down and you need to think a lot about. Okay.
Is it like, the little g, is it like the 9?
Okay, if you take the mass of the Earth and the average radius of the Earth times 6,67 times 10 to the negative 11, you work out G, you get approximately 9,8. Yeah. Now, in actual fact, if you work it out properly, you actually get 9,8 because the distance between us and the center of the Earth varies depending upon where you are on Earth.
But that is, isn't that's the gravitational?
Yeah, that's not the gravitational force, the gravitational field strength. So it's the gravitational constant. Gravitational constant is not the force. The force is the mass times the gravitational constant. When you've done Newton's second law, F net is mass times acceleration. F net equals mass times gravitational acceleration. That gives you gravitational force. So when it comes to this section here, right, if you have to work out accurately the values of G in different parts of the world, you actually get varying values because different parts of the Earth, where surface of the Earth is at different distances from the center of this Earth. As a matter of fact, ladies and gentlemen, if the difference in G between Johannesburg and Cape Town is in the 4th decimal place. They differ by about 1. Okay, now, all right, what I want us to do is I want you to attempt these. Now, Marco, but we haven't done an example. Let me tell you, we've done plenty. Because in actual fact, let me show you here. I'm going to give you some structure. An asteroid series has a radius of 550 kilometers. You need to convert this 2 meters. And a mass of that. What would be the acceleration due to gravity on the surface of Ceres? You are going to work with G equals the mass of the source, which is Ceres, over the distance. So you've got to use the gravitational, universal gravitational constant. It's going to be big G, mass of Ceres divided by the radius, because you're working on the surface, so it's going to be d squared, which is the radius. But now notice, you're working with the acceleration, you're not working with the force. So you first work out G. Now they ask you, what would be the Syrian weight of a person with a mass of 90 kilograms? Now you go and say, well, okay, we know force equals weight, which is the mass of the person, okay, of mass. So there's the mass of the person in the field times G, which you've now worked out G in the A part. So the first thing you're doing here is you're working out the strength of the gravitational field on the surface without working with a force. You're working with the mass of Ceres, which is a planet. I think it's a moon, actually, if I'm not mistaken. It's an asteroid, divided by its radius squared. That gives you the gravitational acceleration or the gravitational field strength. Once you've worked that out, you multiply it by the mass to get the force or the weight. Remember in grade 8, we gave you this. We said G equals 9,8. Or on the moon, G is 1,67. Now you're in grade 11. Now we're going, now you've got to work it out based on the mass and the radius. Okay, so if I can ask you to please do 1, do 2, and this one is a proportionality one. You're not going to like it. But the mass increases by 90, and the diameter or the radius increases by 10. So it's going to be 90 over 10 squared, which is 90 over 100, which is a factor of 9. But I want you to work with that. It bends your mind, but then again, gravity bends space-time. So have a nice, that was a corny joke. I do apologize. Have a wonderful evening. Okay. I will post this. Okay. Now, next week, I actually don't see you next week because it's a public holiday. So what I will do is I will post a recording. I will record the lesson. Okay. Cool. Have a wonderful evening. And those of you who struggle with your calculators, please come and see me. I will gladly help you now. I will gladly help you. Thank you very, very much.